welcome to the 10th lecture of the course Turbulence. So, let us start with a brief recapitulation whatever we have learnt in the last class. So, in the last class mainly we have talked about turbulence modeling. So, in the process of discussion mainly we discussed the algebraic model, but we mentioned there are mainly there are many turbulence model, and those turbulence model can be grouped in 4 categories mainly. So, those are, for example, that we said that algebraic model, then we said that one equation model based on a model energy equation. Okay. Then we talked about, or we mentioned, 2 equation model okay. Then last one we talked about second order closure model. Okay. So, mainly we have talked about the first one, which is the algebraic model, and we said to discuss about this model and this model as well as this model, we need to first develop the kinetic energy equations. Okay. So, that is what we have to work with. So, in the algebraic model we have talked about that based on this Bosenic eddy viscosity approximation and considering the kinetic theory of gases, first we found that mu can be that dynamic viscosity of gases can be written as half rho V thermal into L mean free path. Okay. So, this is what we found using kinetic theory of gases, right. Then from this argument, I mean using the similar argument, we wrote that nu t also can be written as your half rho V mix and L mix. Okay. Whether we can write that nu t half rho V mix and L mix. So, that is what the argument. So, we found that from Prandtl solution that V mix he considered to be constant into L mix into du dy. Okay. So, keep it in mind that V thermal is the thermal velocity. Okay. Thermal velocity of molecules, and L m f p that mean free path. Okay. And V mix is mixing velocity, and L mix is mixing length scale. Okay. So, this is the idea whether we can write the eddy viscosity mu t like this or not. Okay. So, while doing so, Prandtl considered that V mix can be expressed in this fashion such that our nu t can be written as half rho L mix square, some constant also should be there. So, just 1 minute. So, constant half rho L mix square du dy, and considering the half and the constant within the definition of L mix, this dut can be written as L mix square du dy. Okay. This is what we found in the last class. Okay. And here there are some implicit assumptions while deriving this particular expression. We assumed that length scale, that mean free path, okay, mean free path is much less than the mean flow length scale. That was one assumption for this nu is equal to half rho V thermal into mean free path, and another one was the time scale, okay, that is your mean free path V thermal, okay, this also much less than the mean flow time scale. Okay. These are the two assumptions which went into the derivation of this particular expression. Okay. That is what was mentioned in the last class. Okay. So, we need to check whether these particular considerations are also valid for this particular expression. Okay. Unfortunately, this is not the case. For example, if you see that your consideration that L mix, as we remember from the last class, can be considered to be proportional to, let us say, for the case of turbulent boundary layer, that your L mix can be considered as 0.41 to y. Okay. That means, it is proportional to the mean flow scale. So, the idea that mean free path should be much less than the mean flow length scale is not going to be satisfied if this is the case. For example, if it is free shear flows, then L mix we have considered to be proportional to delta. That means, that L mix we are trying to express in terms of the mean flow scale itself, which is that means that L mix is of the order of the mean flow length scale, but while deriving this particular expression from the kinetic theory of gases, we consider that mean free path is much less than the mean flow length scale. So, this particular assumption is not valid for the case of this Prandtl mixing length theory. Similarly, if you consider this particular assumption, that is your time scale should be much less than the mean flow time scale, which is also not the case, because if you remember that Prandtl postulation is V mix is basically proportional to L mix constant into L mix into your this gradient, right. So, this says actually your L mix by V mix, which is the time scale proportional to, is this. Okay. So, here also it is not that that the time scale is not matching the criteria that it should be much less than the mean flow time scale. So, these are the two implicit assumptions which were there while considering the kinetic theory of gases, but this is not the these assumptions are not valid for this particular calculation of mu t. Okay. Nonetheless, although these considerations are not as per the kinetic theory of gases, but still it has been seen the success, I mean it has been found that this mixing length hypothesis or this particular nu t expression works well for many flows. Okay. that we will see later on, as I have mentioned in the last class. So, today mainly we are going to talk about the kinetic energy of turbulence. Okay. So, kinetic energy of turbulence. So, here we are going to talk about two types of kinetic energy of the mean flow and kinetic energy of the turbulence. Okay. So, there are two type of energy equations, and today mainly it will be bit algebraic, because we are going to derive these two equations and then slowly we will start discussion considering both these equations. Okay. So, we are going to talk about kinetic energy. Okay. So, or energy equations. Okay. This will be our topic of today's discussion, right. So, to start with, what we will do, we will consider the that Ram's equation, that Reynolds average Navier-Stokes equation. So, let us consider Reynolds average Navier-Stokes equation. Okay. So, if we consider the momentum equation, which can be written as rho u j, okay, which is the mean velocity, del capital U I del x j equals to our right hand side, this is going to be sigma I j plus tau I j, or we can also write this as rho u I u j u I del x j equals to, we can write this as del T I j del x j. Okay. Here that sigma I j is equal to, if you remember, capital P delta I j plus twice mu capital S I j, right, and tau I j is nothing but your minus rho u I u j. Okay. So, this is the mean stress tensor above one, sigma I j, capital sigma I j, and tau I j is your turbulent stress tensor, and both are symmetric as can be found from this. Okay. So, your T I j, we have already mentioned that T I j is the total stress tensor, which includes both pressure, viscous as well as turbulent, right. So, that means T I j is nothing but sigma I j plus tau I j, which is nothing but your minus capital P delta I j plus twice mu capital S I j plus minus rho u I u j. Okay. So, this is what is your capital T I j. Now, what we will consider, we will multiply this equation by u I. So, multiplying the above equation by capital U I, okay, we get. So, what do we get? If we multiply by U I in both the side of this equation, we get capital U I rho u j del U I del x j equals to, you see I can write this as u I del T I j del x j. I can write like this. Okay. Now, you see u I u j del u I del x j. So, this particular term, you see what I can write, rho u j del half u I such that if you do the derivative of half into u I, you come up with this rho into u I u j del u I del x j. Okay. So, let us modify this particular or let us write it once again. From this equation onward, if you write, then rho u j, and this we can write half capital U I del x j equals to U I T I j del x j. Okay. So, you see what is this particular term half U I. So, half U I square or half U square, which is nothing but the kinetic energy. So, U j into del kinetic energy del x j is nothing but the change of the kinetic energy due to space, because it is the convective part of the total derivative. So, this change is due to the convection of the energy. Okay. So, or convective changes of energy. The temporal part of this particular one is absent in this particular case, that is all because of the fact we have considered a stationary turbulent flow. If we would have considered non-stationary turbulent flow, then we would have we would have got the temporal part of this change of kinetic energy as well, which would have been non-zero. Okay. Please keep it in mind. Since we have considered the stationary turbulent flow, the temporal part will not remain in the left hand side of this equation, right. So, this is essentially change of kinetic energy in space, it does not matter, but we will call this as change of kinetic energy due to what? Due to this right hand side. What is this right hand side? What is this del tau I j del x j? This is the stresses per unit volume. Okay. So, stresses per unit volume, what stresses? T I j. What is T I j? T I j includes pressure stress, viscous stress and Reynolds stress. Okay. So, sort of total stresses. So, that means, and this particular part is basically forces in unit volume. Okay. Forces in unit volume is this. So, forces in unit volume into U I, what is? Force work done per unit time. So, rate of work done. Okay. So, that means due to these changes is occurring in the left hand side, right. So, now this particular work done can be written in this fashion. Okay. So, this equation let us write once again as rho u j del half u I del x j equals to, I can write this as T I j u I del x j, you see. Then I can if I just expand this particular one, then one term is this, another term will come extra, and that is what we are subtracting here, and that term is nothing but T I j del u I del x j. Okay. So, that means work done per unit volume, rate of work done per unit volume can be divided in two parts. One part is this, another part is this. What is this particular part? You see, if you notice that I is also repeated index, j is also repeated index. So, above you consider that I and I, its repeated index. So, that above quantity is nothing but T 1 j u 1 plus T 2 j into u 2 plus T 3 j into u 3. Derivative with respect to j. So, j, what is that? It is just like your divergence, right? Del u I del x I del u j del x j, this is your continuity equation is equal to 0, means divergence is equal to 0. Here I am not saying 0, I am saying this is the divergence of this energy. Okay. So, what is this particular So, this is work done by the stresses on the surfaces of the control volume or on a particle. Okay. How? Because this is what? It is a divergence, and divergence of any quantity. So, in a side note, so this is divergence T I j u I del x j volume equals to, we can write surface, okay, u I T I j u I T I j then n j d s. Okay. So, what is this? So, we can write this particular term is equal to this, and what is this? What is this? You see, work done on the surfaces of the control volume, right, and that on the surfaces of the control, work done due to these turbulent stresses on the, not turbulent stresses, due to these total stresses on the surfaces of the control volume, that is this. That means, this is basically your transport. Okay. So, if suppose your tau I j or u I j, either of these quantities is 0 on the surfaces of the control volume, then this part is 0. What it says? Essentially what it says that transport is 0, means it changes due to this particular term, it locally it can change the energy from one point to other point, or at a particular point energy can change locally. But if you consider the entire control volume, since if divergence is 0, means this particular contribution of this term is 0. That means, locally the energy can changes due to the transport to the inside the control volume, but net change across the control volume is 0, okay, provided tau I j or u I is 0 on the surface of the control volume. Okay. So, that is the implication of this first term, okay, since it can be written as this surface integral. Okay. So, this is the first one. What is the second one? Okay. Second one is what? Second one is your deformation work. Why? So, for example, let us take a Couette flow, okay, a simple Couette flow. Let us say this is a moving plate, okay, this is a moving plate, and in Couette flow the velocity profile is linear, something like this. The mean velocity profile, let us say it is something like this, all right. So, if this is the case for Couette flow, if you consider this particular equation, okay, for Couette flow, if we consider this particular equation, you will figure it out that left hand side, please you take this as an exercise. So, for Couette flow, this distance is actually your x 2 and this distance is x 1, okay, and this is your u velocity, and u here is nothing but a function of x 2 only. Okay. So, you see your in this particular case only non-zero part of the tau I j is T I j is T 1 2, okay. Only non-zero part is T 1 2 for this particular case. If this is the case, this particular equation for this particular case, it will show or it will come as 0 is equal to this particular part T 1 2 u 1 del x 2, okay. This is the only part, and this is T 1 2 del u 1 del x 2. Okay. This is what is going to come. So, what it says, for a Couette flow, the change of kinetic energy at a particular point is 0, because whatever energy is transported to that point is lost to the deformation work. So, that these two terms balances. That is why there will not be any change of kinetic energy. Another point is important to note here, that T 1 2 is basically constant for this particular case. Okay. So, T12 for this particular case is actually constant. So, what is that? P delta ij, okay, plus twice mu capital Sij minus rho ui uj, right. Now, T12, so that means this part is 0, right, because pressure gradient in the Couette flow, consider that pressure gradient to be 0. So, this term is not there at all. Okay. That means you have T12 means only S12 is will survive, all other term will not be there. So, this is 1 and this is 2. Okay. If this is the case, then S12, what is S12? Okay. And let us say your turbulence part is also turbulence is also not there. So, in that particular case, or if it is in that particular case, what you are going to get S12. So, this particular part is equal to essentially your mu d u dx2. Okay. So, you see why this is constant? Why this is constant? Because the shear in this particular part, if it is non-turbulent flow, then turbulent part is also 0. So, in that particular case, this is constant, the shear is constant, du1 dx2 is constant. So, mu into this is constant. So, that means tau T12 is constant for a laminar Couette flow. Okay. So, that means T12 is constant, and constant into this particular part is what? du1 dx2 is deformation, right. So, the moment this is non-zero means there is a shear is present, that means there is a deformation of the fluid particle. So, force, this is force per unit area into the distance. So, this is also work done, but work done by a constant force, because T12 is constant. Work done by a constant force cannot accelerate a fluid particle. So, that is why that this whatever energy needs to be transported, that needs to be balanced with this particular part. Okay. So, this is the one point to note here, and another interesting point is also needs to be discussed, and let me do that. So, this equation can also be written as, you see, rho uj del ui del xj equals to, you see, we can write this as ui del xj, and this particular part can be written as Tij, and this particular part, let me just keep this as, so this particular part can be written as Sij. Okay. Why? So, that needs to be found why. Okay. So, that is because you see, we can write B is equal to, let us say, Tij your del ui del xj, and you see your del ui del xj, that can be written as half del ui, sorry, capital del ui del xj plus del uj del xi minus half del ui del xj minus del uj del xi. Okay. Because you see, this two part will cancel out, and half sorry, this should be plus. So, this two part will cancel out, will be left with half, this of this. So, that is equivalent to your del ui del x j. So, that means this particular part is what? Your capital S I j plus this particular part is, let us call this as A I j. That means, we can write this del ui del x j is equal to your S I j plus A I j, and you see S I j is symmetric. Okay. If you change I and j, I is equal to j or j is equal to I, then you are ended up, or you will end up with the same expression, whereas this is not the case. If you change j is equal to I and j is equal to I and I is equal to j, then you will end up that A j I is equal to minus A I j. Okay. So, this is symmetric and this is anti-symmetric, right. So, that means your B, which is a scalar here, because you see I is repeated index and j is also repeated index. So, B is nothing but your scalar. So, that scalar, then now we can expand as this particular part can be written replaced with that S I j plus A I j. Okay. And since so this is nothing but your T I j S I j plus T I j A I j. Okay. And in this particular case, both I and j are repeated index or dummy indices. Since they are dummy indices, it does not matter, we can also write B is equal to, so B is equal to can be written either this, or B is equal to can be written as T j I j I plus j I A j I, nothing. I have just changed I is equal to j is equal to I, then also it remains scalar, then this expression is this. Okay. So, that is what the point. Anyway, so now what we would like to do, let us say our B is equal to this, and let us call this equation 1. Okay. Now, you see, if we start this equation 1, so start with this equation 1, then we come up with what? Let us find it out. Okay. I have already mentioned that your A I j from this particular expression, if you replace j is equal to I and I is equal to j, then you will come up this, if you replace the or change this I and j, then you will get that A I j is equal to minus A j I. So, I can write this as j I as A I j equals to minus j I. Okay. This is the reason, right. Now, what about this? These are all symmetric tensor. So, S I j, as I have mentioned you, if you change that position, if you change I with j and j with I, then you still come up with the same expression. So, it is symmetric. Similarly, if you check your T I j, if you check your T I j, that will also come as same thing, S capital S I j minus rho u I u j bar. So, this is Reynolds stress tensor, which is symmetric, S I j is symmetric, delta I j is symmetric. So, this is also symmetric. That means, T I j, since it is symmetric, T I j, so from this particular part you can write S I j is equal to S j I and A I j is equal to minus A j I, j I, and from this you can write T I j is equal to T j I. Okay. So, I j is equal to, because there are symmetric. Okay. So, that means you can replace, so this, since they are symmetric, we can write as this j I without changing sign, okay, j I. Okay. Now, in the last expression you see both I and j are dummy indices. So, let us now replace I with j and j with I. If we do that, then this is going to be T I j, that is what I have mentioned at the beginning, if you can remember. So, S I j minus T I j A I j. Okay. So, you see B is equal to, this is what we have got earlier. Now, again B is equal to, we are getting this. So, let us say this equation, is 2. Okay. So, if you add equation 1 and equation 2, then you will be able to come up with the fact that, so adding equation 1 and 2, adding equations 1 and 2, we should be able to write what? B equals to T I. So, B is equal to, we started with del u I del x j, which we could write as T I j S I j plus A I j, which is nothing but your T I j S I j. Okay. Or there is no need to write this particular part. So, from this conclusion we can write this is equal to nothing but your T I j S I j. Okay. So, that means when you are multiplying T I j with the velocity gradient tensor, which is having two parts, symmetric and antisymmetric, only the symmetric part of the product remains, antisymmetric part of the product becomes 0. Okay. Please do keep it in mind, because this is necessary for our further calculation. All right. So, that we understand now how this term comes as this, right, in the mean flow energy equation. So, let us once again come back to that energy equation derivation. So, now we can write this as rho u j u I del x j is equal to, I can write this, right, and this is equal to, you see I can replace the value of T I j and I can write P delta I j u I plus twice S I j u I minus rho u I u j bar capital U I del x j minus T I j. Once again I would like to put the value of T I j. So, that means the second part of this equation becomes minus P delta I j S I j, okay, plus twice mu S I j minus rho u I u j capital S I j, okay, bracket close. Okay. So, now if we simplify, we write rho j del u I del x j, okay. This equals as what? This equals as your del x j minus P delta I j u I. So, the non-zero part of that particular term will be only when I is equal to j, because delta I j is there. So, that means P u j, this is the term which is going to survive, plus twice mu S I j, twice mu capital S I j u I, okay, minus rho u I u j bar u I. So, this part and the other two part you see is going to be minus twice nu capital S I j and plus rho u I u j capital S I j, and the pressure part is 0, because you see why pressure. So, if you consider minus P delta I j S I j, so delta I j non-zero only when I is equal to j, correct. So, that means minus P delta I j S I j. So, let me just tell you this algebra. So, why this part is 0? Minus P delta I j S I j, this is 0 why? P delta I j is non-zero only when delta is equal to, only when I is equal to j. That means P, this is the only part, okay. And what is S I I? S I I P, okay, half del u I del x I, del u I del x I, and what is this? This is continuity. So, that means minus P del u I del x I, which is nothing but from continuity, since it is an incompressible flow, this is the continuity equation. So, this equals to minus P or this equals to nothing, just simply it is 0 from the continuity. Okay. So, that is why the pressure part does not come in this multiplication. Okay. So, this is what is our basically mean flow energy equation. Okay. Let us call this equation number 3. Okay. So, this is what is our mean flow energy equation, and we need to understand what are those terms. Okay. So, you see this particular part once again comes as divergence of this particular quantity. Okay. So, this divergence of anything is nothing but your transport. Okay. So, the first part of this particular term is work done by pressure. Okay. So, work done by pressure, this one is basically viscous transport, okay, which is this one, this is the transport due to Reynolds stresses. Okay. So, transport due to viscous stresses, transport due to Reynolds stresses, right. And what about this term? The last part of this, see this last two term came from this particular term, okay, these two term. If you see here, okay, this is coming from this term. What is this? So, we said this is the transport term, basically transport term, because it can be written, you know, this is because this is nothing but your divergence. Okay. So, this is the transport, and what about this? This is the deformation term. Okay. So, this is work done by these stresses on the fluid particle, okay, on the fluid particle. So, this is essentially your deformation work. Okay. Due to this deformation work, actually what happens, you know, due to this deformation work, your heat, you know, the energy transported to or energy converted to into heat. Okay. So, this last two term in this particular equation 3, this is and this is coming from that deformation term. Okay. So, this is this deformation and this there are two types of deformation. You see S I j and S I j, this is quadratic in S I j. So, this is always positive. So, negative of that means this particular part. So, this particular part is actually, so this particular term is negative. So, means what? It is draining out the energy. It is draining out the energy due to this particular deformation work, and this is negative. So, it is kind of drain of energy due to this work, and this is what is known as dissipation. Okay. So, this is known as dissipation, and this particular part you see, when Sij is positive, we have argued in some previous class, Ui and Uj, this correlation is going to be negative in most of the cases. So, for a positive Sij, this is going to be negative. So, this part or this term is also going to be negative. That means, this is also somewhat is draining the energy or draining the mean flow energy. Okay. So, where it is going? So, due to this drain, this actually turbulence is getting this energy. So, that energy is getting drained from this mean flow, and we expect this particular term to be, it is going to be negative here. So, this particular term is going to be negative. So, this particular term we expect to be positive in the turbulent kinetic energy equation. This is the mean flow kinetic energy equation. Now, we will talk about the turbulent kinetic energy equation, then it will be clear to us. Okay. So, anyway, so these terms, the change of energy in the left hand side is essentially due to this transport by pressure, viscous and Reynolds stresses, due to this drain of energy due to this dissipation. So, this is the dissipation of energy actually. Okay. This particular part is essentially dissipation of energy due to deformation work, and this is also deformation kind of work due to Reynolds stresses. Okay. So, these two are going to drain out the energy because they are negative. Okay. So, they are actually draining the energy. Where it is going, this is transforming into heat, and this one is going to the turbulence. That is what we are going to see. Okay. So, now we will keep this equation in mind. Now, we will work with the the fluctuate the turbulent kinetic energy equation, which is very important to understand. Okay. So, now we are going to talk about turbulent kinetic energy equation. Okay. So, before we discuss this equation, we need to derive this equation. Okay. So, we will start with the instantaneous Navier-Stokes equation. So, instantaneous Navier-Stokes equation, as you can remember, ui tilde del t rho uj tilde del ui tilde del xj equals to, let us write this as sigma ij tilde del xj. Okay. Where this sigma ij tilde, okay, this is nothing but your p tilde del ij plus twice mu sij tilde. Okay. So, this is what our instantaneous kinetic energy equation, sorry, instantaneous momentum equation, that is what I have written. Now, what we would like to do? We would like to multiply this equation in both the sides using ui tilde, and let us see what we get. So, multiplying by ui tilde, we get. Okay. So, if you multiply, then rho ui tilde del ui tilde del t rho ui tilde del ui tilde del uj tilde will also be there, xj equals to ui tilde del sigma ij tilde del xj. Okay. The right hand side of this instantaneous Navier-Stokes equation has been written in this particular term, means force per unit volume for some benefits in the algebraic manipulation of this energy equation. Now, what we do, using Reynolds decomposition, we take the time average of this particular equation. Okay. So, using Reynolds position and taking time average, we get so this particular equation then can be written as ui rho ui plus ui del ui small ui del t bar plus rho ui small ui uj small uj del capital ui small ui del xj bar. Okay. So, equals to what you get capital Ui small ui del capital sigma is a small sigma is a del xj bar. Okay. So, here we have taken the time average in both the sides of this equation, then we have distributed this time averaging over each and every terms. Okay. Now, let us call this first term. Okay. This is the second term and this is the third term. Okay. And if we use the if we go ahead with the algebra of the first term, let us see what we get. So, this is rho ui. So, first term, you consider the first term rho ui del ui del t plus capital Ui small del small ui del t plus small ui capital del ui del t ui del ui del t and time average of this quantity, right, equals to what? That means, this time average is distributive. So, you can write time average of this part is nothing but your this plus ui del t this ui del t this plus ui del t is this. Okay. So, you see this is what mean stationary turbulent flow, mean does not change with respect to time 0. Mean can be used as a coefficient because it does not change with time. What about the derivative of this? The derivative of mean of the derivative of this fluctuation is equal to the derivative of the mean of the fluctuation, which is equal to 0. So, this is equal to 0. In same argument, this is also equal to 0. What about this quantity? This can be written as del half ui into ui. So, ui square del t. So, ui square means ur square bar. Okay. We are talking about stationary turbulence, means that particular average quantity should not change with time. Any statistical average should not change with time. So, this should be 0. So, the first term, so contribution of this term is then 0. Okay. So, first term is 0. Okay. So, now let us start with the second term, which is bit lengthy, but let us do it. Okay. So, if we start with the second term, so this is equal to 0. Okay. 0 plus second term. Let us see what the second term comes. So, second term, if you consider the second term, you see that can be written as rho ui uj ui small uj plus small ui capital uj small ui small uj. Okay. This is into your del ui small ui del xj. Okay. Time average of the entire thing equals to, you see there will be total 8 terms. So, let us just find the 8 terms separately, rho ui uj del ui xj plus rho ui uj del small ui small xj. Okay. So, time average of these, time average of these plus this is over. Now, this one rho capital ui small uj del ui del xj plus rho capital ui uj del small ui xj, right, time average of this, time average of this, plus we are done with this term, we are done with this term, now this term. So, this is going to be ui capital uj del ui del xj plus ui capital uj del small ui del xj plus, okay, plus ui uj del capital ui xj bar plus ui uj del small ui xj, right. Let us see what we get in the next line. Okay. So, you see this quantity, what is this quantity? So, in the next line, let me write here itself for easier understanding. So, next line, let me write it here. So, this one you see ui I can write. So, this rho uj can be written as del ui into ui, such that the moment you do the derivative of this, you end up with this term. What about this term? This is 0, because only one fluctuating quantity here, and this is not a function of time, not a function of time. So, this is a fluctuating quantity which is a function of time, the average of that should be 0. Same argument here, this one is non-zero. Okay. So, the next term which is going to be this, and this is going to be, you see this term we can write as rho, that uj I can take it inside. So, I can write this term as ui outside, and this can be written as del minus rho ui uj bar, okay, del xj. Why? J I can take it inside, because then del ui uj, then one part del ui del xj plus another part del uj del xj, correct. which is from continuity is 0. That is why I can write this. Okay. So, that means the second term is this. So, let me remove this for better understanding. So, plus anyway, which is going to be something here. So, plus, so this term is over. Now, we are left with this term. Once again, time average of this. So, only one quantity which is fluctuating in nature. So, time average of this is 0. Okay. So, that terms also is not there. U I, so sorry, the rho is missed. Okay. So, rho is missed here, I am sorry. So, rho should be here, rho, because we are multiplying by rho, right, rho and rho. Okay. What about this term? This particular term we can write as you see rho u j del half u I bar del x j, just like the capital U I. Okay. And what about this quantity u I u j del u I del x j. So, this is nothing but your plus rho u I u j del capital U I del x j. Okay. So, this is your this term, and we are left with the last term plus the last term, let me write here. So, last term you see what I can do, using the continuity argument j can be taken inside. So, we can write rho u I del u I or either way. So, I can take u I inside first. So, I can write rho u j del half u I into u I del x j. Then using the continuity argument j also can be taken inside. So, that means this particular term can be written as del rho half or you can keep the rho outside maybe u I u j bar del x j. Okay. So, that is your the last term. Okay. So, this is what you get from this second term in the right hand side. Okay. From the second term in the right hand side, this is what we get. Okay. So, this needs to be kept. Okay. So, second terms, so this particular terms gives this, okay, the total. Now, we are left with the last one, right. So, last one let me write it here. Okay. So, the third term, we need to do this algebra for the third term, and that is nothing but your u I plus u I, right, and del sigma I j plus small sigma I j del x j bar. Yes. So, this can be written as you see u I del sigma I j del x j u I del small sigma I j del x j small u I del capital sigma I j del x j plus small u I del small sigma I j del x j, okay, and time average of each and every individual term. And time average of this is nothing but your u I sigma I j del x j, and time average of this of course is 0, as you understand, because this is a fluctuating quantity, this is a mean quantity. So, only one fluctuating quantity, time average of this is 0. What about this? Time average of this is also 0, and we are left with the last part of this. Okay. So, the last part of this is u I del sigma I j del x j. Okay. This is what it is, right. And while deriving the mean flow energy equation, we have already worked with this particular term. Okay. So, we have already worked with this particular term, So, that will work little later. So, let this term be as it is. Let us work with this particular term, okay. And this particular term, you see I can write this particular term can be written as, you see. So, this particular term can be written as, so u I del sigma I j del x j, okay, plus this term can be written as, you know, del sigma I j u I del x j minus sigma I j del u I del x j, okay, bar, right. That is what I can do. And you see this, using this particular, you know, argument that sigma I j, what is sigma I j? Small sigma I j, have I written there anywhere? No. So, small sigma I j, which I have not mentioned here. So, small sigma I j, just like your previous case, P, which is the fluctuating quantity, delta I j plus twice mu small s I j, okay. That is what is your small sigma I j, where that delta P is fluctuating quantity, delta small s I j is also fluctuating strain rate tensor, right. If this is the case, then you see this is also a symmetric stress tensor. If it is a symmetric stress tensor, then this particular quantity can also, we can also write as, you know, what is that, symmetric plus the velocity gradient tensor, which is nothing but small sigma I j into small s I j, just from your previous argument. That means, our third term, essentially our third term, let me write it here since I do not have space. So, our essentially a third term is becoming what? Third term, we can write this as, you know, u I del sigma I j del x j plus, you see that third term I can write is that, let it be for the time being like this only, otherwise we will have some issues. So, x j, and this finally we can write as sigma I j small s I j bar, okay. So, this is what is our third term, okay. So, now if you write the entire equation, then what do we get? So, in our next line, so first part is 0, second part is this, equals to the third term, which is what? Which is nothing but your the algebra what we have done there, and that is basically your u I del capital I j del x j plus del sigma I j u I. Let me just take this outside of this, because it will help us doing the algebra, and the next part sigma I j small s I j bar, okay. So, this is what is our entire equation after doing this operation, okay. So, now you see this particular part in the right hand side. Let me write the right hand side of this equation. So, right hand side can be, you know, simplified. So, right hand side we can write it as this particular term. Similarly, using this we can write as you know, sigma I j u I del x j minus, similarly that sigma I j capital S I j, and this one we can write it as this del x j sigma I j I, okay, bar minus sigma I j small s I j bar, okay. So, we have to just replace the value of capital sigma I j small sigma I j, and we have to, if we do that, let me just do it here. So, if I do it here, then you see in the left hand side I am going to keep only two terms, rho u j del half u I del x j plus rho capital U j del half small u I bar del x j, all the term I would like to write in the right hand side of this equation. If I do so, then what are the terms that I have to take in the right hand side of this equation? Let me just figure it out from here. So, what we are essentially doing, we are going to keep this term in the left hand side, we are going to keep this term in the left hand side, all other term we are going to write in the right hand side. That means, this term goes, that means our three terms goes in the right hand side of this equation, right. So, let us write those three terms. So, if we do that, then this is going to be minus. So, that means, this is going to be your u I del minus rho u I u j bar del x j, this term has gone, then minus rho u I u j bar del u I del x j, that is going as negative, and another term is also going as negative, that is minus rho del half rho, sorry, you can take the rho inside, rho u I u j bar del x j. Okay. These are the three terms which is coming from the convective term in the left hand side of the equation, equal plus, now plus we are going to have other term. So, plus so it is a huge equation. So, let me write this particular term in the extreme left. So, plus so that is going to be negative, right. So, that means if I take in the other side, it is becoming negative. So, that I can write as x j rho u I half should be there u j bar. Okay. So, this is what is going to be the term in the right hand side, the three term from the convective term plus the rest of the term, which are basically a bit lengthy, but nothing to worry about it. So, the other term is going to be your del capital sigma I j into u I, which is nothing but your p delta I j into u I, which we have already talked, that is nothing but your p delta I j plus twice mu capital S I j capital u I. This is what is going to be there in the first part of that equation, minus sigma I j capital I j, sigma I j capital I j. So, that is the pressure part is going to be 0. So, you are going to minus twice nu capital S I j capital S I j, right. Then what we are left with, then another plus term is your minus p small u I bar, okay, plus twice mu small I j u I bar, okay, del x j and minus what we are left with, so the pressure part of that term is going to be 0. So, we are only going to get minus twice mu small S I j bar. Okay. So, this is the entire equation. Now, you see from this particular equation, let us say this equation 4. Okay. From equation 4, if we subtract equation 3, from this equation we can subtract equation 3, then you see what are the terms which is going out from this equation. These are the terms this is the only term which is going out from the left hand side, and what are the other terms which are going out from the right hand side, that is what we have to look at, right. So, this term is also not going to be in the right hand side, this term is also not going to be there in the right hand side, then this 2 term is going to remain, okay. This 2 term is going to remain, and just 1 minute, there is somewhere. So, this is going to come inside this is going to be there minus this particular term, that means one Reynolds term, oh yes. So, this is what what our equation 4. Now, you see these 2 term if you look at, then we can write. So, we can simplify this equation little more. Okay. So, what we can do, considering these 2 term, we can write these 2 term as your you see that minus, that means we can write this as del minus rho ui uj capital Ui del xj, these 2 term. Okay. So, then you see essentially this particular equation 4, let me write it here for clarity. Okay. So, for clarity let me write the equation this equation once again here. So, that means I will get in the left hand side of this equation as capital Uj del Ui del xj plus rho capital Uj del half ui bar del xj. Okay. So, this equals to the right hand side, what I can do, I can write this as the first 2 term in the right hand side of the equation 4 can be written as rho ui uj bar capital Ui del xj. Okay. We can write the first 2 term in the right hand side as that, and if we essentially after this we okay plus sorry, then after that minus del xj half rho ui uj bar, all other things will remain as it is, okay, plus this term plus your minus p del uj twice mu capital Sij del ui, okay, del xj minus twice mu capital Sij capital Sij, okay, plus you see this term as well as this 2 term, this particular term can be taken inside. Okay. So, that means we can just write this as del xj minus p ui bar plus twice mu small capital small uij then ui bar, you see I can take this minus. So, this can be taken inside minus this can be written as rho ui uj half should be there, half this. Okay. So, then this term will not be there in this equation plus this, okay, and minus, you see there are other 2 terms then. So, other 2 terms are minus twice nu capital Sij and plus, sorry, this is also negative twice mu small Sij bar. Okay. So, let us say this is what is our equation 5. Okay. So, equation 5 we have got. Now, if we subtract equation 3 from equation 5, we get, so let me write it, subtracting and 3 from equation 5, we get, if we do that, then finally we get this, okay, ui bar xj, okay, and left hand side minus p ui, sorry, it should be p u j, okay, I am sorry, plus twice mu small s I j small ui bar, then minus half rho ui uj bar. This is the transport term of the fluctuating kinetic energy plus, okay, not plus there will be other two deformation work, that is going to be your twice mu small s I j. So, rho should be there here, okay. I forgotten to keep the rho here. So, small s I j bar minus we are going to get rho ui uj bar del ui, or this is essentially, you can write capital U I j. Okay. So, this is our equation 6 and this is what is your turbulent kinetic energy equation. Okay. So, the turbulent kinetic energy equation is this, which includes transport term, because this is also divergence of this summation of these three quantities, then minus twice mu small s I j small s I j, which is nothing but your deformation work, okay, which is known as dissipation, and this is your deformation work, but this is your production term. Why? As we mentioned, for positive s I j u I u j bar will be negative. So, that negative minus this negative, sorry, negative and negative will be positive. So, this term is going to increase the energy, okay. It is going to help to increase the energy. Okay. So, that is why we call this particular term as production term, and this particular term was there as positive in our first equation, means in our equation 3, that is the mean flow kinetic energy equation. So, this is our mean flow kinetic energy equation, where this deformation work you see that it is negative, because u I u j is mostly negative when s I j is positive. As a result, the entire term is negative, means it is going to help drain the mean flow energy. Okay. Where it is going then? It is going to the turbulence, because this particular term is coming as negative in the fluctuating kinetic energy equation. Okay. So, now we will the derivation of both these equations are over, and we will discuss these two equations in details in the next class. Okay. Equation 3 and equation 6. One is your one is your mean flow kinetic energy equation, which is this one. This is your mean flow kinetic energy equation. Okay. Equation 3, your mean flow kinetic energy equation. So, this is essentially your so mean flow energy equation, okay, and this is known as kinetic or turbulent kinetic energy equation. Okay. Turbulent kinetic energy equation. Okay. So, these are the two equations which we could derive today. We will discuss further about these two equations in the next class. Okay. Today we do not have time anyway. Thank you.